I'll be presenting about Smart Factory IoT project. This project is about building a smart factory using IoT. It focuses on connecting machines, collecting data, and using the data to improve manufacturing. Real world learning. This project is not just theory, it shows how we go from a basic idea to a fully connected factory system in real life. The main challenge is the gap between the software data systems and the machines or the factory equipments. These usually don't communicate well, causing inefficiency. So, the main goal is to connect all the machines, turn isolated system into a single smart system, use data for better decisions. More than 65% of the digital projects fail because systems are not connected properly. So, having a clear system design is very important. IoT architecture overview. A smart factory works in different layers. Each layer has a role and all layers must work together properly. Reference architectures. These are the standard designs or the blueprints. They help in scaling the project from a small test setup to a fully factory. Key layers. The main layers are machines and connectivity, which transfers data. Edge, that is processing the local platform, acts as a cloud, and the user interface, which are the applications. All these layers work together. Cross-cutting concerns. These are important factor across all layers. Security, which protects the data, and the system work together, monitor everything. Sensor and data collection. Sensors acts like the nervous system of the factory. They collect data from machines continuously. Smart sensor selection. Choosing the right sensor is very important. Wrong sensors can lead to wrong data and project failure. Data volume reality. Factories generate huge amount of data. Example, 200 machines generate around 400 gigabytes data per day. So proper planning is needed. Communication standard. Here, MQTT is used to send data. It is lightweight, fast, and works well for IoT systems. Arduino Uno and embedded system. These are like the brains on the factory floor. They process data and control devices. Edge computing. Most data, like 80 to 90%, is processed locally at edge. This reduces delay, saves cloud cost, and gives faster responses. Modern PLCs and real time processing. Real time processing, some actions need instant response like safety system. So processing must happen immediately, not in the cloud. PLCs are industrial controllers. Modern PLCs can act as an edge device and connect with IoT systems and provide flexible automation. Cloud integration. Cloud platforms store large data, analyze data, and provide insights across multiple factories. ThingsBoard. ThingsBoard is an IoT platform used for visualization, data collection, and device control. Microsoft Fabric. It handles very large data processing. Example, Microsoft Fabric can process 1 million plus events per hour. Remote controlling and monitoring. Operators can monitor machines remotely, make quick decisions, and control systems. Digital feedback loop. Data is continuously used to improve processes, optimize performance, and make quick changes. Azure IoT operations. It helps in managing edge devices, monitoring machine performance, and calculating the efficiency. Proactive alert system sends alerts when something is wrong. This helps in quick fixing and reducing the downtime. Skills develop. This project helps learn IT and IoT, that is integration, data system designs, and real world IoT implementations. The main key takeaways from this project is the important learnings, which are very strong architecture is very important, system must be scalable, security is critical, and the final result of the smart factory is higher efficiency, predictive maintenance, and better decision making. This project shows how IoT can transfer a traditional factory into smart, efficient, and connected system. Next will be continued by my friend Sahana.
We can monitor the production unit here, and we can see many other codes like sensor managers, config.h, and other codes. And we compiled here, and it is compiled without any error. And similarly, the node 2 code, which is used to monitor the warehouse, and this is the code. And here are the other codes along with that, like sensor manager, config.h, and more others, like other code like. And it is compiled without any errors here also. This is the Pixim lab, and here we have implemented the production line here, and here monitoring here, and this is the virtual terminal, machine control, vibration sensor, and LEDs, and LM35, DHT22, and relay status. And I am opening now things board cloud now. And here we open the things board cloud in the devices, and we can see the production line here, and it is active now. It's loading. In the latest telemetry, we can see the status of the sensors in the production unit. You can see the LM35 status reader, and we are going to dashboard again, and we are, as I said, we are going to the dashboard of this production unit. Here we have the device to scale the temperature, humidity, and we have the time series chart which has the which has the value of the temperature LM35, and for every time. In the machine status, relay state, switch control, and we can see that production unit line is in the critical condition. Now we will see the warehouse implementation. Virtual terminal is open here now. These are the connections. And we given to the things board. We go to the devices, and if we go to the warehouse, we can see both devices are active. In the telemetry we can see that in the telemetry we can see that the door is open. See, we can see the LDR open, you can see that motion is detected or not. Again we came to the Pixel lab. Again we can lower the value of the DHT and turn on the PIR sensor. I mean click on the PIR sensor and make all the values high. We can see the status here in the things board, in the devices, where in the in the dashboard we can see the temperature scaling, humidity, LDR value, LDR, humidity, row status, HDR, so we can see the conditions here, note of the node to here. And